There's something heavy about a wool blanket at night. Not uncomfortable, just present, like weight that reminds you you're still here, still in a body, still somewhere. I don't know why that's the thought I keep coming back to before starting this. Maybe because what we're about to sit with is almost the opposite. Something with no weight at all, no body, no stillness. Just motion, only motion. Always motion. The sleepy physicist has been a quiet corner for a while now, and it remains that quiet, unhurried, entirely self-funded. If this kind of slow science means something to you, Patreon is where you can help keep it going. A genuinely small gesture that carries more than it probably should. The people who already do that, you know who you are. Thank you. It steadies things. Tonight we're sitting with one of those facts you've heard so often it stopped feeling strange. The speed of light. The cosmic speed limit. Nothing can reach it, nothing can pass it, end of story, except that's not really the end of anything. That's where the interesting stuff starts, actually. I used to think the speed of light was a rule, like a law posted on a highway, something the universe invented to keep things orderly, a ceiling, and I carried that idea around for years, never once noticing how little sense it made. Because rules get broken, rules get amended. Rules exist because something might otherwise violate them. But this isn't that kind of thing. It doesn't work like that at all, and realizing that even slowly, even incompletely, changes the feeling of the whole thing. So here's a question worth sitting with before anything else. What does it mean for a limit to not just exist, but to be unavoidable? Not rhetorical, or maybe it is. I genuinely don't know the cleanest way to answer it, and I'm not going to pretend otherwise. Speed as a concept feels obvious. It's how fast something goes. You've felt it. The lurch of a car accelerating, the way the window landscape blurs, the pressure of movement against your chest. Speed is one of those ideas that seems to need no explanation. And yet it has this hidden requirement that almost everyone forgets almost immediately. It only exists relative to something else. Speed is not a property of a thing. It's relationship between a thing and a point of reference. Your car is fast compared to the footpath. The footpath is slow compared to the car. From space, both are hurtling around the sun at roughly 100,000 kilometers per hour, and neither of them feels anything. This becomes important, quietly, patiently important, later. For now, just let it sit. What's strange about the speed of light is that it doesn't play by that relational rule. Not because someone decided it shouldn't, just it doesn't. You measure the speed of light standing still and you get a number. You measure it while moving toward the light source and you get the same number. You measure it while moving away at any speed you can achieve, in any direction with any instrument, and the answer does not change. 299,792,458 meters per second every time, always. That's genuinely strange. Not fascinating in the polished science communication way. Strange in the way that makes you want to sit down and re-examine something you thought you understood. It means the speed of light isn't fast the way a train is fast or a rocket is fast. It's not competing in the same race. It's something else entirely, something that seems to sit outside the normal vocabulary of motion and just hold still at full speed forever. Here's where I used to get tangled. I kept asking why. Why that speed? Why not faster? Why does light get to be special? And those are fine questions, curious questions, but they have this way of pulling you toward the wrong door. The more useful question, the one that actually leads somewhere, is not why that number, but why does a fixed number exist at all? What kind of universe requires that something move at exactly one speed and no other? The universe, it turns out, is the kind that does. There's a tendency to describe the speed of light as a wall, as a barrier. I've done it myself, probably will again before this is over, but I keep wanting to correct that framing. A wall implies something behind it, something you could reach if the wall weren't there. The speed of light isn't hiding anything. There's no secret space on the other side where faster-than-light travel is happening without us. The limit isn't external to reality. It's more like a property of what space and time are made of. It's baked in, not enforced, just there, the way geometry is there. That's a hard thing to feel the shape of, and I won't pretend it becomes fully comfortable. What we'll move through together over the next few hours is the slow accumulation of how we found this out, not as a triumphant march toward truth, but as something messier, a collection of uncomfortable measurements, a teenager on an imaginary train, a pair of researchers who spent months expecting a result that never arrived, and one quiet paper published in 1905 that didn't announce itself as anything particularly important. The limit on the speed of light is one of those things that turns out to be not a restriction, but a description of what space is, of what time is, of the relationship between matter and energy that holds every atom in your body in the arrangement it currently occupies, which is, okay, that's a lot, and we're not going to get there all at once, though. For now, just the question, just the strangeness of a rule that isn't really a rule, and the wool blanket weight of being somewhere, being someone, in a universe that has decided, or was simply built such, that nothing in it will ever outrun the light. Long before anyone measured it precisely, light was simply assumed to be immediate. It came from the sun, it bounced off walls, it filled rooms, that it had a speed at all, that it took any time whatsoever to go from here to there, was not a settled fact. It took noticing something going slightly wrong somewhere unexpected in the movements of something very far away. Römer had a problem with the moon, not a poetic problem, a genuinely irritating, logistical, won't-leave-you-alone kind of problem. The moon was Io, one of Jupiter's, the innermost one, the punctual one. And it kept showing up late. Not dramatically late, not catastrophically, just off. Enough that you couldn't blame the instruments, by enough that it had to mean something. It's 1676. The observatory smells like tallow candles and cold stone. Ola Römer has been watching Io disappear behind Jupiter and reappear again, over and over, logging the intervals, expecting the kind of clockwork regularity that celestial mechanics had always promised. And the regularity is there. Mostly. But there's this stubborn low-grade wrongness that builds across months. When Earth is moving toward Jupiter, Io's eclipses arrive a little early. When Earth is moving away, they drag behind schedule. The discrepancy isn't random noise, it accumulates. Then it reverses, then it accumulates again. He sat with that for a while, I imagine. The obvious explanation, the one Römer eventually committed to carefully, with what I suspect was some private reluctance, was that light takes time to travel. When Earth is farther from Jupiter, the light carrying the image of Io's reappearance has more distance to cover. It arrives late not because Io is late, but because the news of Io takes longer to reach us. Simple, almost too simple, except that almost nobody before him had seriously entertained it as a working physical fact, rather than a philosophical curiosity. I want to stop here for a second, because I think there's something genuinely underappreciated about what that realization requires. It requires believing that your instruments are right, that the discrepancy is real, that the universe is doing something, Not that you made an error somewhere in 17 months of careful notation. That takes a certain, stubbornness. The comfortable assumption, the one that doesn't unsettle anything, is always, I made a mistake. Römer didn't take that door. His estimate for the speed of light was wrong, incidentally. Not embarrassingly wrong. He got the order of magnitude, which is, honestly, extraordinary for the tools available. He thought light crossed the diameter of Earth's orbit in about 11 minutes. The real answer is closer to 16.5. But the wrongness of the number is almost beside the point. What mattered was the claim that there was a number. That light was not instantaneous, that it moved specifically at some finite measurable rate through space. People didn't immediately agree. That seems obvious in retrospect. New ideas rarely land clean, but it's worth sitting with. There were serious astronomers, serious thinkers, who looked at Römer's data and decided the discrepancies were more plausibly explained by irregularities in Eo's orbit than by the travel time of light. Not because they were careless, because the alternative required accepting something that had never been demonstrated directly, only inferred from the behavior of a moon around a planet 600 million kilometers away. That's a long inferential chain to hang a fundamental claim on, and the honest answer is, they weren't entirely wrong to be cautious. About 50 years later, a very different kind of confirmation arrived. No moons, no planetary distances, just a telescope in England, a man named James Bradley, and the strange, persistent wrongness of a star. Bradley was trying to measure stellar parallax, the tiny apparent shift in a star's position caused by Earth's orbital motion. He didn't find parallax, he found something else. The stars were displaced from their expected positions, but the displacement didn't behave the way parallax would. It was rotated 90 degrees from what it should have been. All the stars showed it. The whole sky was, in a quiet, systematic way, tilted slightly wrong. He spent, I think it was 2 years, working through what this could mean. What he eventually landed on is called aberration. It's easier to feel than to define. When you're moving through rain, you tilt your umbrella forward. The rain isn't falling at an angle. You're moving into it. The faster you move, the more you tilt. Stars behave the same way because their light takes time to travel and Earth is moving. The apparent position of a star shifts slightly in the direction of Earth's motion, just as the apparent angle of the rain shifts when you run. What Bradley's aberration gave the world was something Römer's calculation hadn't quite managed, a confirmation that didn't rely on one particular moon, one particular planet, one particular set of accumulated delays. It was structural. It was everywhere all at once, written across the entire sky. Light travelled at a finite speed, not fast enough to be instantaneous, specific, bounded. The number he derived was closer than Römer's, still not exact by modern standards, but close enough that it was clearly the same thing being measured. Two independent methods, neither designed for this purpose, arriving at the same uncomfortable conclusion through completely different logic. That's the kind of convergence that doesn't feel like coincidence. Here's what I find genuinely odd about this whole stretch of history. And I realise odd is doing a lot of work there, but I can't think of a better word. For most of human existence, nobody needed the speed of light to be a specific number. It was either infinite, which simplified everything, or it was so fast that the difference was academic. Aristotle thought it was instantaneous. Descartes thought it was instantaneous. Kepler, who spent his entire career mapping the exact mechanics of planetary orbits, operated perfectly fine with an infinite light speed. The universe ran without it. Then someone noticed a moon was late. And then someone noticed the rain was falling at the wrong angle. And suddenly there was a number, imprecise, contested, inconvenient, sitting in the middle of physics, refusing to be theoretical anymore. What nobody knew yet, in the century following Bradley, was how deep that number went, how load-bearing it would turn out to be. A finite speed of light seems, at first, like a practical fact, a measurement, a useful quantity for calculating when a signal will arrive, or why the sun you see is 8 minutes in the past, not now. Useful, fine. It takes a while to understand that it isn't just a measurement, that it's more like a seam in the fabric of things, that pulling on it, really pulling mathematically carefully, unravels assumptions about time and space that nobody had thought to examine because they seemed too obvious to question. But that comes later. For now there's just the number, wrong by a bit, right in kind, pulled out of the behaviour of a distant moon by a man in a cold observatory, candle guttering in the draught from the door, probably tired, probably not fully aware that the irritating small wrongness he was trying to account for would eventually reach all the way down into the structure of reality. He just needed Io to make sense. There was a next step, and it came from a different direction entirely, not from observation, not from telescopes or moons, but from the mathematics of fields and waves, and from a Scottish physicist who wasn't looking for a speed limit at all. There's a specific kind of tiredness that makes the ceiling interesting. Not sleeplessness, more like the end of a long day where your body has stopped asking for things and your mind is just running on its own loosely without agenda. I think about speed on nights like that. Not intentionally, it just surfaces. The fan in the corner cycling at the same rate it always does. The particular nothing of a room that isn't going anywhere. Speed feels obvious until you try to hold it still. Everyone has a rough working definition, how fast something moves, how much distance it covers in how much time, distance divided by time, clean, finished. The kind of definition that feels like it closes a door, except it doesn't, quite, because it contains a word that does a lot of invisible work. Relative to what? You're on a train, moving at say 100 kilometers per hour. The person in the seat next to you is also doing 100 kilometers per hour on same train, same velocity, same direction. Relative to you, they are perfectly still. They are not moving at all. And that's not a trick of perception. That's not an approximation. That is physically, accurately, completely what is happening. Their speed relative to you is 0. Their speed relative to the platform you just passed is 100. Both numbers are correct. Neither is more real than the other. I used to think this was just a technicality, something philosophers cared about that physicists could safely ignore in unpractice. It isn't. Here's the thing that took me an embarrassingly long time to internalize. There is no such thing as absolute speed. There is no master reference frame, no special, fixed, cosmically preferred point of view from which the true speeds of all objects can be measured and ranked. Newton wanted there to be one. He called it absolute space, this vast, still invisible backdrop against which all real motion could be measured. It was a beautiful idea. Orderly, satisfying, it made the equations clean. And it is, probably, as far as we can determine, entirely fictional. Everything that has a speed has it relative to something else, only relative to something else, always, which seems fine, which seems like a quirk you can work around, until light. Here is where the strangeness accumulates, quietly and without warning. Imagine. And this is the kind of thought experiment that sounds almost too simple, which is exactly why it's worth taking slowly, Imagine you're standing still and you fire a pulse of light forward. It leaves at 299,792,458 meters per second measured from your position. Standard, expected. Now, imagine you're in a spacecraft, moving toward the same destination at, let's say, half the speed of light. You fire the same pulse. Logic, the ordinary intuitive Newtonian logic that governs every other moving thing, says the pulse should now be travelling at 1.5 times the speed of light relative to the destination. You added your speed to the light speed. That's how addition works. That's how boats and rivers work, how baseballs thrown from moving cars work, how every compound velocity you've ever experienced in your entire life has worked. The light does not do this. It still travels at 299,792,458 meters per second from your moving frame, from the destination's frame, from any frame. It does not accept the additional velocity. It does not combine. It just goes at the same speed, indifferent to the motion of whatever produced it. And that's, I keep wanting to reach for a comparison here, something that makes it feel less strange, but every comparison I come up with breaks down in the middle and becomes more confusing than the original thing. So I'll just leave it as what it is. It's strange, specifically stubbornly strange in a way that doesn't soften with familiarity. This is the part where I want to be honest about something. I think most people, when they first encounter this, perform a kind of cognitive courtesy. They nod, they accept it, they file it under weird quantum stuff, which isn't even the right category, but it's a comfortable draw, and they move on. I did that for years. The constancy of the speed of light was a fact I carried without ever really feeling the full weight of what it meant. Because what it means is this: speed as a concept works differently for light than for everything else. And that difference isn't incidental. It's structural. It implies, and this is the part that takes a while to land, that the measurements of distance and time that produce that speed must themselves be doing something flexible, something accommodating, something that adjusts behind the scenes to keep that number constant for every observer. Which means distance isn't fixed, which means time isn't fixed, which means the clean, settled, perfectly intuitive world where a meter is always a meter and a second is always a second is not wrong exactly, not in everyday life, not at the speed you'll ever actually travel, but incomplete, a very good local approximation, an extremely useful fiction at human scales. There's a cold cup of tea on the desk right now that I keep meaning to do something about and keep not doing, and I mention it only because it feels right to be sitting somewhere specific while saying this. The idea that even the room around you, the ordinary geometry of walls and right angles and the reliable distance between 2 points, is not the final word on how space behaves. It's just what you get at low speeds in a weak gravitational field. The ordinary regime, and it's fine, it works, you can build buildings in it, but it isn't fundamental. The thing I keep returning to is this: speed requires 2 ingredients, distance and time, and if both of those are negotiable, if they stretch and compress in response to relative motion, then speed is not the solid, intuitive, stable quantity it presents itself as. It's a ratio of 2 malleable things, and for most objects, that malleability is so small it's invisible, but for light the malleability isn't small, the malleability is the whole story. The universe doesn't keep the speed of light constant by setting a speed limit. It keeps it constant by adjusting the measurements. Space contracts, time dilates, whatever it takes, and out the other side, always the same number. That's not a rule, I want to say it's more like a symptom. a symptom of something deeper about what space and time actually are, about the relationship between them, about the geometry that underlies all of this. We're not quite there yet. The geometry comes later. For now, speed is a relationship, not a property. And light, in its refusal to behave like a relationship, in its absolute insistence on the same value from every vantage point, is quietly telling us that space and time are not what they appear to be from inside a room with a cold cup of tea at the end of a long enough day. The first people who tried to prove this flexibility, who looked for concrete evidence that Earth's motion through space should change the measured speed of light, designed one of the most careful experiments in the history of physics. They were trying to detect a difference. They found none, which turned out to be the most important result they could possibly have produced. The building still exists. That's the first thing I think about when I come back to this experiment. Not the physics, not the results, just the fact that there's a physical place where this happened. Case Western Reserve University in Cleveland. Stone walls. A basement chosen specifically for its stillness, its insulation from the vibration of street traffic above. You can picture it, the particular cool dampness of a below-ground room in late spring, the smell of machine oil and sandstone, two men working in near silence around a device that sat on a 5-foot square slab of marble floating in a trough of liquid mercury, Albert Michelson and Edward Morley, and an apparatus so obsessively precise it almost feels aggressive about it. The thing they built, and thing is the right word here I think, because calling it simply an interferometer makes it sound cleaner than it was, more theoretical, when in reality it was this painstaking, fussy physical arrangement of mirrors and half-silvered glass and wooden arms. The thing they built was designed to detect a difference in the speed of light depending on which direction it was travelling relative to Earth's motion. The logic was clean, almost irresistible. If light travelled through some medium, the luminiferous ether, as it was called, this invisible, universe-filling stuff that everyone assumed light must be waving through the way sound waves through air, then Earth's motion through that ether should create a kind of headwind effect. Light travelling in the direction of Earth's orbit would be fighting against the ether current. Light travelling perpendicular to it would be crossing the current. The two beams should arrive back at the detector slightly out of step. The interference pattern, those alternating bands of light and dark that appear when two waves are even fractionally misaligned, would shift when they rotated the apparatus. A tiny shift, but measurable. With this device, absolutely measurable. Michelson had already tried a version of this 5 years earlier, got a result that was suggestive but inconclusive, so they rebuilt the whole thing. Bigger, more stable, floated on mercury so it could rotate smoothly, continuously, without introducing vibration. They ran it for days, different times of day to account for Earth's rotation, different seasons to account for different orientations relative to the orbital direction. They were meticulous in a way that feels almost anxious in retrospect, like they knew how much was riding on it, and wanted to make absolutely sure that when they found the result they expected, nobody could argue with the method. The shift they were looking for was tiny, a 40th of a fringe, roughly. The apparatus was sensitive enough to detect a 20th of a fringe, meaning they had built into their margin twice the sensitivity they needed. They weren't operating at the edge of their instrument's capability. They had room, and the fringe didn't shift. Not in the way they expected. There were small variations, there always are, with physical equipment in a real room, with temperature fluctuations and the distant rumble of a wagon on the street above, but nothing systematic. Nothing that built across rotation angles, nothing that reversed when they reversed the apparatus. The interference pattern sat there, largely stable, and refused to show them the ether wind. I want to be careful here about something, because I think this moment gets narratively tidied up in a way that isn't quite honest. The result was not immediately understood. It wasn't a clean, triumphant, here is the answer moment. Michelson himself, who had spent years on this, who had staked real professional credibility on its sensitivity, reportedly described it as a failure, not a discovery, a failure to detect what he was looking for. He kept trying to explain the null result away, returning to the experiment, running variations, because the alternative, that the ether simply wasn't there, that light didn't need a medium, that its speed was genuinely constant regardless of the observer's motion, was not a conclusion the existing framework had any room for. It took years. Other theorists, other frameworks, the result sat in the literature, slightly uncomfortable, slightly unresolved until the theoretical machinery caught up to it. Here is the central metaphor I keep coming back to, and I'll use it once and then let it go. Imagine you're trying to measure the current in a river by timing how long it takes to swim across and back versus upstream and downstream. You do the calculation, you swim the course, and the times are identical, set in both directions, at every angle, in every season, which means either the current doesn't exist or you're somehow moving with the river in a way that makes detection impossible. The ether version of that second option was attempted. Several physicists proposed that Earth might drag the ether along with it, like a boat pulling water. But that explanation created new problems faster than it solved the old one. The cleaner answer was simpler and more unsettling. There was no current. There was no river. The medium that everyone had assumed light must require didn't exist. Light wasn't a wave in something, it was, and this is where the language genuinely struggles, it was just a wave, self-propagating, requiring nothing to move through, and its speed, in the absence of a medium to provide a reference, was the same from everywhere. That's the result. Dressed up and made respectable by a decade of theoretical work, that's what 1887 produced. Nothing. They measured nothing. And the nothing turned out to be one of the most structurally important results in the history of physics, not because of what it found, but because of what it ruled out so cleanly that the ruled out thing never really recovered. What I find hard to fully absorb even now is the specific texture of what Michelson and Morley were working against. They weren't being incurious, they weren't resistant to strange answers. They were operating inside a framework so coherent, so well supported by everything else they knew, that the null result didn't feel like a window opening. It felt like a wall where a window should have been. The ether wasn't a fringe idea. It was load-bearing. It was the reason light could be a wave, because waves need something to wave through. Remove it, and you have to explain what light is waving through. And the answer? Nothing. It's waving through nothing. The electromagnetic field is its own medium, required a complete reconception of what fields even are. That work wasn't done yet. Couldn't be done yet. The experiment produced a result that the available theory couldn't metabolize. So it sat, quietly wrong-fitting, an anomaly that everyone could see and nobody could quite solve, until someone could. The someone was not a professor, not a working experimentalist with an institution and a grant and a marble slab floating in Mercury. He was a young man in a patent office in Bern, Switzerland, examining other people's inventions all day, and thinking about light on his own time, specifically about what it would look like if you could somehow move alongside it. Start with something small, a sound. You're standing on a platform and a train passes, not slowing, just passing, full speed, and there's someone on that train is playing music. You've heard this before, lived it probably, the way the pitch bends downward as it moves away from you. The note leaving the speaker is fixed, the source is moving, and the wave, the actual pressure wave travelling through air toward your ear, gets stretched by the recession, arrives at a lower frequency than it was produced. The source was doing one thing. You received something different. The motion of the source changed what you got. That's the Doppler effect. It applies to sound. It applies in a modified form to light. The light from galaxies moving away from us shifts toward red, stretched by recession. All of that is real. All of that happens. But here is what doesn't happen with light, the thing that separates it from the train and the music and every other wave you've ever encountered. The speed doesn't change. The frequency shifts. The wavelength stretches or compresses. The color changes. The energy changes. The speed, the raw rate at which the wave moves through space, stays exactly where it always is. A sound wave from a moving train reaches you faster if the train is coming toward you. Slightly, measurably, the wave crests pile up in front of the source, and the whole wave front advances faster than it would from a stationary emitter. Basic mechanics, expected. The motion of the source adds to the motion of the wave. Light doesn't do that. Fire a photon from a stationary source, fire one from a source moving toward you at 90% of the speed of light. Both photons arrive at the same speed, not approximately the same. Not close enough that the difference is negligible, identical. The motion of the source contributed exactly nothing to the speed of what it emitted. I remember the first time this was explained to me properly, and I nodded and moved on and later realized I hadn't actually absorbed it at all. I'd processed the words without sitting with the implication, because the implication is genuinely odd and it requires, I don't know, a particular quality of attention that doesn't come naturally, at least not to me. The implication is this: light, from the moment it's produced, has no memory of where it came from, not in any mystical sense, just physically. The photon doesn't carry the velocity of its source. It doesn't inherit momentum in the direction of travel, the way a ball thrown from a moving car inherits the car's speed on top of the throw. It leaves at sea, always at sea, from a star moving toward us at half the speed of light, from a galaxy receding at nearly the speed of light, from a flashlight sitting still on a table. The photons depart at the same rate. The source's motion is simply not a variable that the speed of light accepts as input. That's the thing I couldn't find a clean analogy for in the last chapter, and I'm still not sure I can. Every analogy involves something that does carry source velocity. Bullets, sound, thrown objects, because those are the things that make intuitive sense to us. Our entire physical intuition is built from objects that accumulate velocities, that combine motion, that remember where they came from. Light is built differently. There's a particular quality to the light coming through a window at dusk. Not sunset, not the golden hour that everyone reaches for, just the flat grey-blue of last light before dark, where the room seems to go quiet in a specific way. I notice it sometimes. The light isn't dramatic. It just fills everything evenly and then slowly doesn't. I think about the photons crossing that distance, 8 minutes and 20 seconds from the sun's surface, completely indifferent to the fact that the sun itself is moving around the galactic center at roughly 230 kilometers per second, that the galaxy is moving, that everything is moving, and yet those photons arrived here at exactly 299,792,458 meters per second, and not a fraction more. The motion underneath them, the source velocity, the galactic drift, the local group's own trajectory, none of it added up in the speed. It couldn't. Light doesn't accumulate. Here is where I want to place the metaphor, because I think it earns its place here rather than earlier. There's a type of river, slow, broad, the kind that looks almost motionless from a distance, where the surface moves at a completely different rate than the current underneath. You can drop something light on the top, a leaf, a piece of bark, and watch it drift. Then drop something that sinks part way, held at mid-depth by its own buoyancy, and it moves faster, caught by the subsurface current. The river has layers of speed. What you measure depends entirely on where inside it you're measuring. Everything we know moves like that river, with layers, with inherited velocities that stack, with speeds that are always relative to the depth you're measuring from. Light moves like something that isn't in the river at all. That's probably where the metaphor breaks, and I know it breaks, but it does something useful before it does. It locates the strangeness in the right place. The issue isn't that light is fast. The issue is that light is exempt from the arithmetic that governs everything else. It doesn't add. It doesn't compound. It doesn't benefit from a running start or suffer from a retreating source. It is in some way that took physics decades to formalize, operating according to a completely separate set of rules. Or, and this is the reframe that eventually proves more useful, it isn't operating by separate rules. It's operating by the same rules as everything else. We just had the rules wrong. We thought velocity addition was simple arithmetic. It isn't. It never was. Light didn't break the rule. Light exposed that the rule we had was only an approximation, valid at low speeds, quietly wrong at high ones. At the speeds light travels, the real rule of velocity addition gives you c, always c. Because the real rule, the one that was always true even at human speeds, even on trains and platforms and in basement observatories, contains a correction factor that becomes enormous near the speed of light and is essentially invisible at anything slower. Light wasn't the exception. Light was the thing that revealed the correction. That's a hard shift to make conceptually. It requires giving up on the intuition that simple arithmetic is a law of nature, rather than a very good low-speed habit. And most of us will never quite feel it in our bones, I think, not fully, not physically. We can hold the logic, we can follow the math. But the felt sense of it, the embodied certainty that moving things add their speeds the way numbers add, that feeling doesn't really go away, which is fine. It doesn't need to. What matters is the structure underneath the feeling. And the structure says, light moves at c, because c is what falls out of the actual equations of motion for something with no mass, no rest state, nothing to refer back to. Not because someone decided it, not because the universe posted a rule, because when you work out what an electromagnetic wave must do, given what electricity and magnetism actually are, the speed is already in there, fixed, derived, inevitable. The number was always in the equations. It just took a while to notice that the equations were telling us something about the universe we hadn't thought to ask. Somebody asked. Not through experiment, not with mirrors and mercury in a marble slab. He asked it as a question about what the equations meant, what it would actually look like physically if you were moving alongside a light wave. And the question once asked wouldn't resolve. It sat with him for years, until it did. He was 16 actually, not 17. I've seen it written both ways and gone back and forth on it. And the honest answer is that the exact age depends on which account you trust and whether you count from when the question first formed or when he first wrote it down in any legible way. 16, 17. The difference doesn't matter, and somehow matters completely, the way the specific age of a person when something permanent happens to them always feels like it should be part of the record. What's agreed on is this. He was a teenager, and he was already thinking about light in a way that most working physicists weren't. The question he asked was, on the surface, almost embarrassingly simple. What would a light wave look like if you were moving alongside it at the same speed? If you matched its velocity exactly, kept pace, stayed level, travelled in formation, what would you see? With sound, this is answerable. Move alongside a sound wave at the speed of sound and the wave appears frozen, relative to you. The crests and troughs sit still. You're riding them. That's what a sonic boom is, in a sense. An aircraft catching up to its own sound, the waves bunching and compressing at the threshold. You can picture it. It has a satisfying physical logic. Light didn't give him that. The smell of Zurich in early autumn is something I've read described as cold metal and bread, not a combination that should work, and yet apparently it does, particularly near the old market streets. I mention it only because Einstein spent years in that city as a student and then, as a young man, quietly failing to find an academic position, and I keep wanting to locate him somewhere real, rather than in the clean abstract space where famous scientists tend to get stored. He was somewhere specific. He was cold sometimes, probably. He ate meals. He was, by multiple accounts, a student who impressed certain professors enormously and irritated others completely, depending on whether they valued the quality of his questions or the reliability of his attendance. The question about light was with him through all of that. Through Zurich, through the frustrating job search, through the patent office in Bern where he eventually landed. A position he got partly through the help of a friend's father, not through any distinguished academic reputation, because at that point he didn't have one. He sat at a desk in Bern examining other people's patents for clock synchronization mechanisms, clocks, of all things, clocks and their coordination across distances, and the light question sat with him. What would it look like frozen? Here is why the question doesn't have a clean answer. Maxwell's equations, the 4 equations that James Clerk Maxwell assembled in the 1860s to describe electricity and magnetism as a unified thing, contain, buried in their structure, a wave solution. They predict that electromagnetic disturbances propagate as waves, and the speed of those waves falls directly out of the equations. It's determined by 2 constants, the permittivity and permeability of free space, 2 numbers describing how strongly electric and magnetic fields interact with the vacuum. You divide them into each other in a specific way, and you get the speed of light exactly without any reference to observers, or reference frames or relative motion. The speed is in the equations themselves, not the speed relative to something, just the speed. Which means, if you moved alongside a light wave at the speed of light, the wave should, by the logic Einstein was working with, appear as a frozen, oscillating electromagnetic field. Static crests and troughs, a wave that wasn't waving. And Maxwell's equations, applied to that scenario, produced something that wasn't physically meaningful. Not approximately wrong, structurally wrong, the kind of wrong where the mathematics isn't giving you a weird answer, it's refusing to give you an answer at all, the way dividing by 0 refuses. A frozen light wave wasn't just strange, it was, in the language of the equations, not a thing that could exist. I want to be careful here. I might be slightly oversimplifying the exact form of his reasoning at 16, because we know it mostly from later recollections, and Einstein's own memory of his own thinking wasn't always a perfect record. He said much later that this thought experiment was the seed of special relativity, that it felt to him for years like a paradox he couldn't escape. That's probably true in spirit, even if the precise logical form of it shifted over time. What I don't want to do is make it sound like the answer came quickly. It didn't. It sat with him for roughly 10 years. 10 years during which physics continued to develop, during which other theorists, Lorentz, Poincaré, were circling the same problems from different directions, producing mathematical tools that would turn out to be essential without quite arriving at the physical interpretation that made them all fall into place. The tools existed before the understanding. That happens sometimes. The machinery gets built before anyone fully knows what it's for. There's a specific quality to a question that won't resolve, and I think everyone has had at least one, not about physics, just about anything. Some personal thing that sits in the back of the mind and resurfaces at odd moments without warning, and resists every approach you try. It doesn't feel productive, it feels stuck. Like a door that responds to every key you own with the same flat resistance. That's the central metaphor here, and I want to use it lightly. The question is a door that doesn't open until you question the door itself, because the resolution, when it finally came in 1905, didn't answer the original question directly. It didn't explain what a frozen light wave would look like. It dissolved the question entirely by showing that the premise was impossible, that no material observer could ever reach the speed of light, and therefore the scenario of riding alongside a light wave could never physically occur. The question wasn't unanswerable, it was unphysical, and arriving at that realization required questioning something so foundational that most people working in physics at the time hadn't noticed it was an assumption at all. The assumption was this, that time passes at the same rate for everyone. Not just an assumption, an axiom, something so woven into the fabric of how physics was done, how equations were written, how experiments were designed, how cause and effect were understood, that it wasn't listed as an assumption because nobody thought it needed to be. It was the water. It was the ground. It was the thing you stood on to do everything else. Einstein questioned the ground, not all at once, not in a flash. The later mythology tends towards sudden insight, the famous story of riding a tram in Bern, looking back at the clock tower, imagining the tram accelerating to the speed of light and the clock face freezing. Good story, probably contains a real experiential core. But the version where enlightenment arrives whole and clean in a single moment is almost always a retrospective compression of something that was actually slow and recursive and full of dead ends. What seems more accurate, and this is the version that feels more useful to sit with, is that the resolution came from finally accepting a conclusion that the evidence had been pointing to for years, but that required giving up something deeply comfortable. The constancy of the speed of light was either true or it wasn't. The Michelson-Morley result said it was true. Maxwell's equation said it was true. Everything pointed the same direction. The only thing in the way was the assumption that time was universal, that simultaneity was absolute, that a clock on Earth and a clock on a moving spacecraft would tick in perfect agreement forever. Give up that assumption, even provisionally, and the paradox dissolves. The door opens, not onto an easy room, onto something strange, vast, full of new questions, but it opens. He gave it up, and spent 5 weeks reportedly writing out what followed. What followed was a paper. 9,000 words, give or take, no citations, no acknowledgement of prior work. A quiet, methodical, almost businesslike dismantling of the conceptual foundations that everyone else in physics had been building on without examining. It was published in June of 1905 in a German journal called Annalen der Physik, and it did not at first make much noise at all. The journal it appeared in was not obscure. That's worth saying plainly because the image of a lone genius publishing in obscurity is almost always more romantic than accurate, and this case is no different. Annalen der Physik was a serious, well-regarded publication, the kind of journal that working physicists read, and the paper went through a real editorial process before it appeared in the June 1905 issue. It was read by people who would have understood it or could have, It simply didn't, for a while, produce the reaction the content probably deserved. I've tried to read the original paper. The German is not the problem. There are good translations. The problem is that it reads like something written by a person who is being very careful not to sound like they're doing what they're doing. It's methodical in a way that feels almost evasive at first, until you realize the methodical quality is the point. Einstein wasn't building toward a dramatic conclusion. He was quietly removing floorboards. The full title, translated, is something like, "On the Electrodynamics of Moving Bodies," not "A New Theory of Space and Time," not "Why Everything You Know About Motion Is Wrong." Electrodynamics of Moving Bodies, a technical title, a title that sounds like a narrow specialist paper on a narrow specialist problem, which is, in one sense, exactly what it is, and in another sense, one of the most catastrophic understatements in the history of scientific publishing. It opens with an asymmetry, not a result, not a claim, an observation about something slightly untidy in the existing theory, a small nagging inconsistency in how electromagnetic induction was described depending on which part of the system you considered to be moving. Move a magnet near a stationary conductor and you get a certain description of why current flows. Hold the magnet stationary and move the conductor and you get a different description, different mechanism, different conceptual story, but identical observable result. The current is the same, the physical outcome is identical, but the explanation changes based on which frame you're standing in. Einstein found this irritating. That's my reading of it anyway. I can't verify his internal state from the text, but there's a quality to the opening paragraph that feels like the specific irritation of someone who has been bothered by something small and wrong-shaped for a long time and is finally putting it on the table, not angry, just done tolerating it. He calls it an asymmetry that doesn't seem to be present in the phenomena themselves. The phenomena don't care which frame you're in. The explanation shouldn't either. That's the seed. Two postulates follow from it. Not derived, not proven from first principles, simply stated as the foundation everything else will rest on. The first postulate: the laws of physics are the same in all inertial reference frames. No experiment, performed entirely within a uniformly moving system, can tell you whether that system is moving or standing still. This isn't new exactly. Galileo understood something like it, and it was embedded in Newtonian mechanics in a partial way, but stating it cleanly as a universal principle, without exceptions, without qualifications, is a commitment. It means there is no preferred frame, no absolute rest, no special vantage point from which the true state of the universe can be read off directly. The second postulate: the speed of light in a vacuum is the same for all observers, regardless of the motion of the source. That's it. That's the whole foundation. 2 sentences, essentially. And then the paper spends its remaining length following those 2 sentences, wherever they lead, with a kind of unhurried, almost bureaucratic thoroughness that, I keep wanting to say it's admirable, but it's more than that. It's strange. It feels like watching someone methodically pull threads from a sweater and lay them on a table and say, "Here, these are what it was made of. I know this is uncomfortable, let's continue." What follows from those 2 postulates, when you actually work through the logic rather than just accepting the conclusions, is a sequence of results that each feel, in isolation, almost manageable, and in combination feel like the ground has quietly relocated. Simultaneity goes first. 2 events that are simultaneous in one reference frame are not necessarily simultaneous in another. This isn't a measurement error. It isn't an artifact of signal travel time that can be corrected for. It's a genuine, physical, irreducible feature of how time works when frames are moving relative to each other. The ordering of events, whether A happened before B or B before A, or both at the same moment, depends on the observer's state of motion. For events that are causally connected, the ordering is preserved. Cause always precedes effect for everyone. But for events that are far apart and close in time, with no causal link between them, the sequence is not universal. Different observers, moving differently, will genuinely disagree, and both will be right. This is the part where most people reading for the first time feel something go slightly wrong in their heads. The instinct is to ask which observer is really right. The answer, and this is the part where you have to sit still and let it land, is that the question doesn't have a privileged answer. They're both right. Not as a philosophical consolation. Physically, structurally, actually right. Simultaneity is not absolute. It never was. We just never moved fast enough to notice. Time dilation comes next. Moving clocks run slow. Not because they're broken, not because the motion interferes with the mechanism, because time itself, the actual passage of duration, the rate at which the universe ticks, is different for objects in relative motion. A clock on a fast-moving spacecraft runs genuinely, measurably, physically slower than an identical clock left behind. When the spacecraft returns, less time has passed on board. The difference is real. The travelling clock and the stationary clock reunited show different readings, and neither is wrong. At ordinary speeds, the difference is so small it's irrelevant. GPS satellites, which move quickly and sit in weaker gravity, accumulate a measurable time difference relative to ground clocks in a single day. The navigation system corrects for it. Has to. Without the correction, the positioning error would grow by several kilometers per day, so this is not theoretical, not abstract. The time dilation that falls out of a paper published in 1905 by a patent clerk is built into the infrastructure of modern navigation, quietly, routinely, because it is simply how time works. Length contraction follows. Objects in motion are shorter along the direction of travel than they are at rest. Again, not an illusion, not a perspective effect. A physical compression of the measured length that depends on relative velocity. At speeds you'll ever experience, it's immeasurable. Near the speed of light, it becomes dramatic. The room where I first worked through this properly, not the textbook summary, but the actual logical sequence, smelled like dry erase markers and the particular staleness of recycled air. A study room in a university building that was newer than it looked on the outside. I remember writing out the Lorentz transformations and staring at the gamma factor, the number that controls how much time dilation and length contraction occur, and noting that as velocity approaches the speed of light, gamma doesn't approach a large number, it approaches infinity, not a big number, infinity, which means the time dilation and length contraction don't approach dramatic but finite values near the speed of light. They approach limitlessness. A clock moving at the speed of light would stop entirely. An object compressed along its direction of travel to the speed of light would have zero length. These are not physical states that matter can achieve. They're all the mathematical boundary of what the equations describe, the wall that the structure of space-time itself erects against any material thing reaching C. The speed limit is not posted from outside. It emerges from inside the mathematics of what space and time are. Einstein's paper doesn't say nothing can go faster than light as a rule. It says, here are the actual relationships between space and time, and when you follow them to their logical end, reaching the speed of light requires infinite energy and produces physically incoherent results. The limit is a consequence, not a decree. What the paper doesn't contain is almost as striking as what it does. No citations. This was noted at the time and has been remarked on since. Lorentz's name appears in the text once, in a technical context, but the vast prior literature on electrodynamics and relative motion, the work of Poincaré and Fitzgerald and Larmor, who had each arrived at pieces of this, goes unacknowledged. Whether this was deliberate or oversight, or the natural result of a mind that had arrived at the same conclusions independently and didn't fully register the overlap, that remains genuinely unclear, and I'm not going to pretend I have a firm view on it. What's harder to dispute is the quality of the thing itself, not its correctness. Correctness can be verified, has been verified, endlessly, but its character. The paper has a particular quality of internal confidence that comes not from assertiveness but from structural coherence. Each step follows from the last. Nothing is hand-waved. The assumptions are named at the start, and then the logic never departs from them. It reads like a person who was not trying to convince anyone of anything, but simply following a trail they had found and recording where it went. The trail went a very long way, further it turned out than even the paper itself described. There was one thing the June 1905 paper didn't address directly, a small loose thread about the relationship between energy and mass that Einstein noticed shortly after publication. He wrote a brief follow-up note, 3 pages, that September. It ended with an equation, 4 symbols. The most recognized mathematical statement in the history of physics, introduced not with fanfare but as a minor addendum, almost an afterthought to a paper that had already changed everything. There's a sound a house makes at 2 in the morning that it doesn't make at any other time, not a loud sound, more like the building settling into itself, joists contracting slightly in the cool, something ticking once in the wall and then going quiet. You notice it only because everything else has stopped. The background noise of the day, traffic, appliances, the particular low hum of people existing nearby, has dropped away, and what's left is just the structure of the place, doing whatever structures do when nobody's asking anything of them. I think about time on nights like that, not philosophically, not existentially, just time as a physical thing, as something the universe is actually doing, not just a way we organize experience, because that's what the last chapter quietly set up, without quite saying it directly. Time is not a backdrop. It's not the neutral stage on which events play out, ticking steadily forward in perfect universal agreement while matter and energy perform their routines. It's a participant. It responds. It bends. And the first real consequence of Einstein's 2 postulates, the one that arrives before energy-mass equivalence, before the famous equation, before any of the later machinery, is that time does not pass at the same rate for everyone. Not approximately, not at high energies only, always, everywhere. The difference is just too small to feel at ordinary speeds. Here is the cleanest way I can put it, and I'll try not to dress it up too much, because dressing it up, I've found, actually makes it harder to absorb rather than easier. 2 clocks, identical, synchronized, one stays where it is, one moves, fast, in a straight line, then returns. When they're reunited, the moving clock shows less elapsed time. Not because something went wrong with it, not because the journey damaged the mechanism, because less time actually passed for the moving clock. The universe, for that clock, between departure and return, contained fewer seconds. That's time dilation. And it is, I keep wanting to say it's as counterintuitive, but that word has been so flattened by overuse that it doesn't carry the weight I need it to. It's more than counterintuitive. It's a direct assault on something so fundamental to how consciousness works that there's almost no mental foothold for it. We experience time as the one thing that isn't relative, the one fixed river we're all being carried down together at the same rate from the same upstream. Birth, duration, death. All on the same schedule, all synchronized, all universal. That feeling is wrong. Useful, but wrong. The mechanism, if you want to call it that, sits inside the structure of what the equations say. Take the gamma factor, the number that keeps appearing in relativistic calculations. The one that depends on velocity and sits under a square root. At low velocities, gamma is almost exactly 1. The correction it applies to time is nearly undetectable. A person walking across a room is aging microscopically slower than someone standing still. Not measurably, not for any practical purpose, but the difference is real and non-zero, and in the right direction, and it scales. As velocity increases, gamma increases, slowly at first. Then, as velocity approaches the speed of light rapidly, steeply, the curve bends upward and does not come back down. At 90% of the speed of light, gamma is a little over 2. A clock moving that fast runs at less than half the rate of a stationary one. Time for that traveller is passing at less than half the rate it passes for you, watching them go. At 99%, gamma is just over 7. At 99.9%, it's around 22. At 99.99%, and I want to resist the urge to keep stacking nines because the point isn't the specific numbers, it's the shape of what's happening. Gamma is over 70. The curve isn't approaching a ceiling, it's approaching a vertical wall. That wall is c, the speed of light. The place where gamma becomes infinite, where time for the moving object would stop entirely. Here's where I want to place the single metaphor and then leave it alone. Imagine stretching a rubber band between 2 fingers. At small extensions, it behaves linearly. Double the stretch, double the force, predictable, manageable, but stretch it far enough and the relationship changes. The last few millimeters before it snaps require disproportionate effort. The band doesn't gradually become harder to stretch. It becomes, to at a certain point, quite suddenly and feel almost impossible. Then it fails. The resistance isn't external. It's in the structure of the material. You're fighting what the rubber is, not what's holding it back. Accelerating matter toward the speed of light is something like that. Not perfectly, the analogy breaks in the details as they all do, but the shape of it is right. The resistance grows, not linearly, not even exponentially in the simple sense. It grows in a way that asymptotes. You can always add more energy. You can always push harder. The object will always get faster in response, but the speed gains shrink while the energy requirements climb, and the ratio between what you put in and what you get out becomes, near the speed of light, essentially everything for essentially nothing. Mass is doing something in that resistance, and the something it's doing connects directly to why time dilation and the speed limit are the same phenomenon described from different angles. The GPS correction is worth sitting with for a moment longer than most explanations give it. 24 satellites, orbiting at roughly 20,000 kilometers altitude, moving at about 14,000 kilometers per hour relative to the ground. The time dilation from their velocity, special relativistic from motion, causes their clocks to run slow by about 7 microseconds per day, relative to ground clocks. Simultaneously, they're in weaker gravity than we are, which causes a different effect, general relativistic, that makes their clocks run fast by about 45 microseconds per day. Net effect, satellite clocks run fast by roughly 38 microseconds daily. 38 microseconds per day. That sounds small, it is small, but GPS works by timing signals with extraordinary precision, and 38 microseconds of accumulated clock error translates to roughly 11 kilometers of positioning error per day if uncorrected. Not 11 meters, 11 kilometers every day. Growing, the correction is applied, routinely. The satellite clocks are intentionally set to run slightly slow before launch so that relativistic effects bring them to the right rate once in orbit. This is not a theoretical nicety. It is an engineering requirement built into a system used billions of times a day by people who have never heard of the Lorentz transformation and have no reason to care that a patent clerk in Bern in 1905 quietly rewrote the operating manual for time. But the GPS example, useful as it is, carries a small risk. It makes time dilation feel like a correction, a small adjustment, a rounding error in the ledger of ordinary life. And at the speeds and scales of ordinary life, that's accurate. The effect is tiny, manageable, easily compensated. What it obscures is the structure underneath. The reason the correction is needed isn't technical, it's fundamental. Time is genuinely different at different velocities, not offset, not delayed, different in rate, different in the number of seconds that actually exist between two events, depending on how you travelled between them. The GPS correction doesn't paper over a measurement problem. It accounts for a real physical difference in how much time passed. That distinction between a measurement error and a real physical difference is where most intuitions stall. Because the only time we experience duration as real is when we live through it. And we don't live at relativistic speeds. We have no felt experience of time compression. We can't remember a version of ourselves for whom time ran slower, then come back and compare notes. The relativity of time is, for us, permanently theoretical in the experiential sense, even when it's completely practical in the engineering sense, which leaves it sitting in this odd space, verified, applied, structurally certain, and at the same time genuinely, possibly permanently outside the reach of direct human intuition. I don't know what to do with that, honestly. I'm not sure there's anything to do with it. What I keep returning to, on nights when the house is making its small sounds and the hour is wrong for anything requiring certainty, is this. Time dilation isn't a consequence of the speed of light limit in the sense that the limit causes it. They're the same thing. Two descriptions of one geometric fact about space-time. The constancy of the speed of light and the relativity of time are not cause and effect. They're facets. Turn the crystal one way, you see the speed limit. Turn it another, you see time doing something it was always doing quietly, in every moving thing, at every speed, in every direction since the universe began. We just needed the right question to notice. The question of energy was the next thing to surface, not dramatically, not as a separate investigation, but as a loose thread Einstein noticed in his own work 3 months after the June paper. He pulled it. What came out was 4 symbols that described in the smallest possible space why the speed of light appears in an equation about mass and energy at all, and why the two, which had always seemed like separate categories, were never separate to begin with. Pick something up. Anything nearby, a book, a glass, your phone. Feel the weight of it. Not think about it, actually feel it. The downward pull against your palm, the small muscular effort of holding it in place against gravity. That resistance is mass. The thing the object has that makes it want to stay where it is, that makes moving it cost something, that makes throwing it harder than throwing nothing. Mass is the most ordinary thing in the world. Every object you have ever touched has had it. It is so constant, so reliable, so completely taken for granted that there is almost no way to make it feel interesting from the outside. And then relativity gets involved. The equation everyone knows is E equals mc squared. 4 symbols. The C in there. That's the speed of light. 299,792,458 meters per second squared, which produces a number so large it barely fits comfortably in the imagination. roughly 89 quintillion 875 quadrillion 517 trillion 873 billion 681,764 in SI units. A kilogram of mass, fully converted to energy, releases that many joules. The sun converts about 4 million tons of mass to energy every second just to keep shining. The number is not incidentally large. The largeness is the point. But the equation isn't really about conversion, not primarily. It's about equivalence. Mass and energy are not two things that can be exchanged under the right circumstances. They are. And this is the part that tends to get lost in the popular version, the same thing in different forms. Energy has mass. Mass is energy. Not metaphorically, not as a useful approximation. Actually, physically, in every interaction always, which means when you heat an object, add thermal energy to it, becomes very slightly heavier. Not detectably heavier at ordinary temperatures, but heavier. A hot cup of coffee has more mass than a cold one. A compressed spring has more mass than an uncompressed one. A charged battery has more mass than a dead one. The differences are so absurdly small, fractions of nanograms, that no scale ever built could measure them for ordinary objects. But the equivalence is real, and it runs in both directions, and it was sitting inside the mathematics of special relativity waiting to be noticed. Einstein noticed it 3 months after the June paper. He wrote a follow-up 3 pages long titled, again with that characteristic restraint, "Does the inertia of a body depend upon its energy content?" The answer, which the 3 pages demonstrated, was yes. Here is where the chapter really wants to go, though. Not to E equals mc squared, which everyone has already met, but to what happens to mass, specifically when something moves. Because there's a version of relativistic mass increase that appears in older textbooks, the idea that a moving object literally becomes heavier as it speeds up, that its mass increases with velocity, that this is what prevents it from reaching the speed of light. And it's not exactly wrong, but it's not exactly right either. And the distinction matters in a way that most pop science explanations quietly skip over. Let me try to say this carefully because I've gotten confused about it before, and I want to be honest about where the confusion sits. When a particle accelerates, when you push it harder, give it more energy, try to get it going faster, what you observe is that the faster it already is, the less additional speed you get from the same additional push. Feed a particle at 10% of light speed, a burst of energy, and it jumps ahead noticeably. Feed a particle at 99% of light speed the same energy and it barely moves. The energy goes in, the speed doesn't come out. Something is absorbing the energy without producing the velocity increase you'd expect from Newton's laws. That something is, depending on how you frame it, either an increase in the particle's relativistic mass, or an increase in its kinetic energy that doesn't convert to speed the way Newtonian mechanics predicts, or a consequence of the fact that momentum in relativity isn't simply mass times velocity, but a more complex quantity involving gamma. All 3 framings are mathematically consistent. Physicists today tend to prefer the third because it avoids the conceptual messiness of a velocity-dependent mass. But the observed effect, the stubborn heavy drag that builds as you push something faster and faster, is real regardless of how you describe it. There's a particle accelerator in Geneva, the Large Hadron Collider, where protons are accelerated to 99.9999991% of the speed of light. That's not a number I'm rounding for dramatic effect. That is the actual operational velocity. At that speed, the protons have a gamma factor of roughly 7,500. Their relativistic energy, the energy that must be supplied to keep accelerating them, is 7,500 times their rest energy. They are, in the sense that matters for the physics of collisions, about 7,500 times more energetic than a stationary proton. The energy of the collision, when two of them meet head-on, is what produces the exotic, short-lived particles that the detectors are looking for. The infrastructure required to reach that velocity is, I want to say impressive, but impressive is a thin word for it. A ring 27 kilometers in circumference. Superconducting magnets cooled to 1.9 Kelvin, colder than the average temperature of deep space because the magnetic fields required to bend the proton path at that speed can only be generated by superconducting coils. Roughly 96 tons of liquid helium for the cooling system. An electrical grid connection that during full operation draws about 200 megawatts. The energy of a small city running continuously to push protons to 99.9999991% of light speed, and still not reaching it, not closer to reaching it in any meaningful sense. Because the remaining gap, that 0.0000009%, isn't a small distance. It's infinite. In energy terms. The curve never arrives. The protons at 99.9999991% are not 9/10 of the way to light speed in terms of energy requirements. They are not even close to the beginning of the final approach. Every additional fraction of a percent would require more energy than the last. The asymptote doesn't soften, it doesn't plateau, it stays vertical. What I find genuinely, there's a word I want here that isn't haunting because that's too much, but it's in that direction. What I find genuinely strange about the LHC situation is the specificity of it. The engineers know exactly how much energy is needed to reach each velocity increment. They can calculate it precisely. The math is clean, unambiguous, confirmed by a century of particle physics. There is no uncertainty about the curve. No room to hope that maybe at very high energies something changes, some threshold is crossed, the asymptote opens up. It doesn't. The physicists at CERN are not pushing against ignorance. They're pushing against a wall they can see completely and map exactly, and will never reach the hay of. That is either deeply discouraging or oddly peaceful, depending on the night. The bedroom ceiling has a small water stain near the corner, left there from some leak years ago, patched but not repainted, oval-shaped, slightly round at the edges. And I've been staring at it while thinking through this chapter because the oval looks, if you squint slightly, like a particle track in a bubble chamber photograph. The kind of image you'd find in an old physics textbook, curving lines in liquid hydrogen, marking where charged particles passed and ionized the medium. Little arcs of evidence, things that existed for microseconds, left traces, and are gone. Those tracks are what the LHC produces in a modernized version. Collision events lasting unimaginable fractions of a second, leaving signatures in detectors that the software reconstructs into something visual. The energy required to produce those events came from pushing protons up that asymptotic curve for months, round and round the 27-kilometer ring, adding speed in the tiniest increments, squeezing every fraction out of the available magnetic field, always approaching and never arriving. The speed of light as a limit is not theoretical to the people who run that accelerator. It's a budget constraint. It's what determines how large the ring has to be, how powerful the magnets, how cold the cooling system, how many megawatts the grid must supply. The limit is in the engineering, in the infrastructure, in the specific price in euros and kilowatts of getting as close as humanity currently can to the speed that nothing with mass will ever reach. The equation E equals mc squared lives at the center of all of this. Not as a formula for explosions, which is how it mostly appears in popular culture, but as a statement about the deep relationship between what a thing is and how much it resists being pushed. Mass is resistance. Energy is resistance. They're the same resistance, showing different faces, and the speed of light, c squared, sitting there in the middle of the equation, is not incidental to the relationship. It is the relationship. The conversion factor that turns kilograms into joules and back again. The number that tells you how much energy a kilogram of matter contains at rest before you've done anything to it, just by existing. Which means c isn't just a speed, it's embedded in the structure of matter itself, in the ratio between what things are and what they can do, in the deep grammar of how energy and mass speak to each other. That's what getting heavier is really pointing at. Not weight, not mass in the simple sense. The way the universe is built such that approaching c costs more, means more, resists more, not because of an arbitrary limit, but because of what energy and matter fundamentally are, and what they have always been, and what they cannot stop being. More energy put in, less speed produced. The returns don't just diminish, they collapse. And to understand what it looks like to approach the edge of that collapse, not in a particle accelerator, but in something you might actually imagine travelling in, something with mass and momentum and a destination, the next chapter has to go somewhere uncomfortable, into the approach itself, into what it costs to cover that last distance between almost and never. There is a particular stretch of interstate highway, somewhere in the American Midwest, where the land is flat enough, and the night dark enough, and the road straight enough, that the headlights reach out ahead of you and simply disappear into nothing. Not into a curve, not into a hill, just into distance that outpaces the light. You could drive for an hour on a road like that and honestly feel like you haven't moved. The destination doesn't get closer in any way you can sense. The darkness ahead stays exactly as far away as it was when you started. I don't know why that image keeps attaching itself to this chapter. Probably because what we're about to sit inside, the approach to the speed of light, the asymptote that never resolves, has that same quality. Not the drama of a wall, not the satisfying finality of a door slamming shut, just an endless road through dark that stays exactly as long as it always was, no matter how fast you go. Start with something manageable, a spacecraft, hypothetical, which is the only kind available for this conversation. It has a mass, it has an engine, it has fuel or some energy source. The specific mechanism doesn't matter yet, so set it aside. It's sitting still, relative to us, and we want to accelerate it. At low velocities, everything behaves the way you'd expect. Energy in, speed out, roughly proportional. Double the energy, nearly double the speed, not quite because the relativistic correction is already technically present. But at low velocities, gamma is so close to 1 that the deviation is invisible. The spacecraft climbs through 10% of light speed. 20. 30. The fuel burns. The speed climbs. The physics is strange in principle and completely ordinary in practice. Then things start to shift. Not suddenly. That's important. There's no threshold you cross, no warning light, no moment where the equations change character. The change is gradual, continuous, and in one direction only. As velocity increases, the gamma factor, that number which controls how energy and momentum and time all behave, begins to pull away from 1. At 50% of light speed, gamma is about 1.15. Modest, manageable. The spacecraft is slightly harder to accelerate than Newtonian mechanics would predict, but the discrepancy is small. At 70%, gamma is around 1.4. At 90%, just over 2.3. At 95%, roughly 3.2. The curve is bending. You can feel it bending even just reading the numbers. Here is where I want to place the sustained image, and I'll use it carefully because it's doing real work here, and I don't want to overload it. think about a shadow. Specifically, think about what happens when you tilt a flat surface away from a light source at a shallow angle. The shadow of an object cast on that surface stretches. At small angles, the stretching is modest. Tilt further and the shadow elongates dramatically. Tilt the surface almost parallel to the beam and the shadow becomes not large, not very large, but infinitely long. It never ends. The shadow of a finite object cast at the right angle runs off the surface entirely and vanishes into theoretical extension. The energy cost of acceleration near the speed of light has that shape. A finite amount of matter, a finite thing, casting an infinite shadow in energy space as it approaches the right angle to the beam. You can pour in finite energy and get real acceleration. Measurable. True, the spacecraft moves faster, but the angle keeps tilting and the shadow keeps stretching and the amount of energy required to produce the next increment of speed keeps growing in a way that is not merely steep, but genuinely asymptotic. The surface tilts toward parallel and the shadow reaches toward forever, and you never quite get there from here. That's where the image earns its place and also where I want to let it go, because the mathematics is cleaner than the metaphor from here on. Let's put numbers to it because the numbers are what make the stomach drop. To accelerate 1 kilogram, the mass of a smallish bag of flour, to 90% of light speed requires roughly 19 petajoules of energy. A petajoule is 10 to the 15th power joules. 19 of them. For context, the atomic bomb dropped on Hiroshima released approximately 63 terajoules, 6.3 times 10 to the 13th power joules. So 90% of light speed for 1 kilogram costs about 300 times the energy of that bomb. For 1 kilogram, to reach 99% costs about 57 petajoules for that same kilogram. 3 times more than 90% for 9 more percentage points. 99.9%, roughly 180 petajoules, another factor of 3 for 1 more percentage point. The pattern is not linear. It's not even exponential in the simple doubling sense. The energy cost is chasing a curve that steepens faster than any fixed ratio can describe, because what governs it is gamma. And gamma near C doesn't grow by a constant factor per step. It accelerates its own growth. Each additional fraction of a percent toward light speed costs more than the last fraction by a margin that itself keeps increasing. For a real spacecraft, something with mass enough to carry humans, which means tens of thousands of kilograms at absolute minimum and realistically far more, the numbers become difficult to write down with a straight face. And that's before accounting for the fuel, which has mass, which itself requires energy to accelerate, which requires more fuel, in the compounding spiral that rocket engineers call the tyranny of the rocket equation, here elevated from a logistical annoyance to a fundamental geometric wall. The world's most powerful particle accelerator, and we visited this in the last chapter briefly, runs on roughly 200 megawatts of electrical power to push protons weighing 1.67 times 10 to the minus 27 kilograms to 99.9999991% of light speed. A proton, the smallest thing the LHC works with, the energy required to push something with human-scale mass to even 99% of light speed, using the most efficient conceivable mechanism, exceeds the total energy output of the Sun over several years. This is not a technology problem. I want to be clear about that because the framing sometimes slips toward, well, maybe someday we'll have better engines, as if the barrier is engineering rather than physics. The barrier is physics. Better engines would help with 1,000 real problems in space travel. This particular problem is not one of them. The energy requirement near light speed doesn't come from inefficiency, it comes from what space-time is. No efficiency improvement touches it. No fuel density improvement reaches it. The asymptote is a property of the geometry, not the technology. The speed of light is not expensive to reach the way diamonds are expensive, because of scarcity, because of market conditions, because of supply chains that could theoretically be reorganized. It's expensive the way infinity is expensive. It doesn't have a price. It has a structure. There's a mug on the windowsill that's been there since yesterday morning, forgotten, still with maybe a centimetre of cold coffee in the bottom, and I keep looking at it all, while I'm working through this and thinking, absurdly, about how completely at rest it appears, sitting there, going nowhere, occupying its own small patch of space-time with total uncomplicated stillness, except it isn't still. It's moving with the Earth's rotation at roughly 400 meters per second at this latitude, moving with the Earth's orbital velocity around the Sun at about 30 kilometers per second, moving with the solar system's velocity around the galactic center at roughly 230 kilometers per second, moving with the Milky Way's own motion through the local group and the local group's motion toward the great attractor, and the whole vast structure of things being pulled and flowing and drifting in ways that don't cancel cleanly. The mug is never still. Nothing is ever still. And yet all of those accumulated velocities, hundreds of kilometers per second of real motion through space, are unnoticeable, irrelevant to its behavior, because they're all far enough below her sea that gamma stays close enough to one that nothing unusual happens. The mug sits, the coffee gets cold at a normal rate, time passes normally, mass behaves normally, the relativistic regime, the place where gamma starts to bite, where time dilates measurably, where energy costs explode, is not a place we ever go, not accidentally, not at the scales of human life. It requires deliberate, extraordinary, essentially cosmic effort to enter it, which is why it took so long to notice it existed. Here is the thing I keep wanting to say and keep approaching and backing away from, because I'm not sure it lands right and I want to be careful with it. The impossibility of reaching light speed isn't at the deepest level about energy. Energy is the symptom. The disease, if you want to call it that, is the structure of space-time itself. Special relativity isn't a theory about speed limits. It's a theory about the geometry of the four-dimensional manifold that matter and energy exist inside. And in that geometry, the speed of light is not a barrier erected at the edge of the possible. It's woven into the definition of what a space-time interval is, what causality means, what the relationship between space and time fundamentally requires. To reach C, you wouldn't just need infinite energy. You would need to become something other than matter, something without rest mass, something that, like a photon, has no stationary state, no proper time, no frame of reference in which it exists at rest. Matter cannot do that, not because it lacks the energy, because it is what it is. The last few percent don't take everything because the universe is stingy. They take everything because they're not really a path to a destination. They're a path to a boundary condition, to the edge of what matter is allowed to mean. You can approach it arbitrarily close. The LHC does it routinely for protons, but the protons never arrive, not at 99%, not at 99.999, not ever. The road stays exactly as long as it always was. The headlights reach out and disappear into the dark, and the destination, if you can call it that, holds its distance with a patience that has no flaw. There is one kind of thing that does travel at exactly the speed of light, not approaching it, not asymptotically near it, exactly it, always, without exception, from the moment of creation until absorption. The photon. And what makes the photon capable of this? what structural property it possesses that matter lacks entirely, opens into a different kind of strange. Outside, somewhere, past the window, a moth is hitting the glass repeatedly. Not hard, just persistent. That soft, irregular tick of wings and body making contact with the surface it can't understand is there. It keeps doing it. The light inside is what it's orienting toward, presumably. Or what passes for orientation in a moth. The light came through the glass. Therefore the glass is not blocking the light. Therefore the glass is not really there. Wrong, obviously, but coherent given the information available. I think about that when I try to approach the photon, not because the comparison holds in any rigorous sense, it doesn't, but because there's something about the photon that produces a similar quality of confusion. It moves through space. It carries energy. It can be detected, counted, redirected. It behaves, in almost every practical sense, like a thing. And yet the category of thing that matter occupies, the category defined by having mass, having a rest state, having a frame of reference in which you sit still and time passes, so that category does not contain the photon. The photon has no mass, not a small mass, not a mass too tiny to measure. Zero, exactly zero. And that zero is not a gap in our knowledge. It's a structural fact about what electromagnetism is, verified to extraordinary precision, constrained by experiment to be less than 10 to the minus 18 electron volts if it exists at all, which is, for practical purposes, for all purposes, nothing. Here is what zero mass means for speed, and I want to say it plainly before surrounding it with anything. For massive particles, the relationship between energy, momentum, and mass produces a rest energy, a baseline amount of energy the particle has simply by existing before you've done anything to it. That rest energy is mc squared, the famous part. A particle at rest still has energy. Its mass is, in a sense, frozen energy, and because it has this rest state, this condition of existing without moving, it has a frame of reference. You can, in principle, move alongside it, match its velocity, sit next to it in space, both of you at rest relative to each other. Time passes for both of you. You can compare clocks. For a massless particle, there is no rest state. Not a theoretical rest state that's impractical to achieve. Not a rest state that requires too much energy to reach. There is simply no such condition. A photon cannot be at rest, not in any frame, not under any circumstances. The mathematics doesn't produce a rest solution. Set the velocity of a massless particle to anything other than c, and the equations return nonsense. Not a small energy, not a large energy, not infinity, but something structurally undefined. Like asking what north of the North Pole is. The photon exists only in motion. Motion at exactly one speed. Always. I used to think this was, honestly, I used to think it was a slightly arbitrary rule, like the universe had just decided photons go at sea the way a country decides which side of the road to drive on. Convention. Assignment. And then, at some point, the actual logic of it settled in, and I realized it wasn't a rule at all. It was a consequence. In special relativity, the energy-momentum relationship for any particle is E squared equals PC squared plus mc squared squared, where P is momentum, m is rest mass, c is light speed. For massive particles, the mc squared term is there, non-zero, providing the rest energy floor. For massless particles, set m to 0, the equation collapses to E equals pc. Energy equals momentum times c. That's it. No rest energy, no floor, just motion all the way down. And when you ask what speed does a particle with zero rest mass travel at, given this energy-momentum relationship? The answer comes out as c, not as a limit, not as an asymptote approached from below, as the exact, necessary, only possible answer. A massless particle moving at anything other than c would violate the energy-momentum relationship. It would be, in the language of what the equations describe, not a thing. So the photon doesn't travel at c because it's fast. It travels at c because c is the only speed consistent with what it is. The strangeness compounds when you try to think about the photon's experience. And I use that word loosely, very loosely, because photons don't have experiences, but the thought experiment is useful anyway. In special relativity, a moving clock runs slow. The faster the motion, the slower the clock. At the speed of light, the clock stops entirely. Proper time, the time measured by a clock moving with the object, then goes to zero. Which means, from the photon's perspective, if you insist on constructing one, which you probably shouldn't, but here we are, no time passes between emission and absorption. The photon leaves a star 8 minutes away and it arrives at your eye, and for the photon those two events are not separated by 8 minutes. They are not separated by any time at all. Emission and absorption are, in some sense, the same moment. The photon does not experience the journey. It does not exist between departure and arrival in any way that involves duration. I want to be careful here because it's easy to make this sound more mystical than it is. The photon doesn't skip the journey. It's not teleporting. The 8 light minutes of space are genuinely there, genuinely traversed. What's absent is the time. The journey takes 0 time in the photon's reference frame, not because the distance collapsed, but because the time did. Length contraction and time dilation, pushed all the way to c, produce a frame in which all distances in the direction of travel contract to 0, and all durations shrink to 0 simultaneously, which is another way of saying a reference frame at c doesn't exist, can't exist. The mathematics of such a frame is undefined in the same way the rest frame was undefined. There is no valid inertial frame in which a photon is at rest, and equally no valid inertial frame that travels alongside a photon. The photon sits permanently outside the family of reference frames that special relativity describes. Not beyond them, outside them. It occupies a different kind of slot in the structure of the theory. What this tells us about mass is, I think, the part that doesn't get enough attention. Mass is the thing that gives particles access to time. That's an odd way to say it, but it seems right to me, or mostly right, with the caveat that I might be framing it slightly too poetically for the physics to fully bear. Massive particles have rest frames. In their rest frames, time passes. They have histories. They persist. They can be here, then there, with the genuine duration in between. Their existence is extended through time in a way that has content, cause preceding effect, one moment following another, a sequence that means something. Massless particles don't have that. They don't persist through time. They transit through space instantaneously from their own non-existent frame of reference and either get absorbed or they don't. There is no in-between for a photon, no idle state, no waiting. Mass, then, is not just resistance to acceleration. It's the thing that buys you a seat inside time, the thing that lets you have a before and after. Here is the soft metaphor, placed here because it's earned rather than decorative. A river has a surface and a depth, things that float, light enough, spread enough to ride the surface, moving fast with the current, touching only the topmost layer of the water. Things with density sink part way, or fully, and interact with the slower, more complex currents below. The surface moves differently than the depth. The surface skims, light skims. Not metaphorically, not quite literally, but in the sense that it moves along a kind of surface of space-time. The null geodesic, the path that has zero space-time interval, the track along which the geometry of the universe is, in a precise technical sense, flat. It doesn't descend into time the way massive things do. It crosses space without accumulating duration. It rides the surface of things. Everything with mass sinks into time, into the slower, more complex experience of existing with a before and a before that, of being somewhere, then somewhere else, with the universe ticking around you the whole way. Gravity wave, not gravitational wave, as those are different. No, I mean the actual photons carrying electromagnetic force. The virtual photons of quantum electrodynamics, which also travel at sea because they also have no mass. There's a whole family of massless particles, and they're all in this same condition. Gluons, which carry the strong nuclear force, also massless, also at sea. The hypothetical graviton, if it exists, also predicted to be massless, also at sea. The pattern isn't a coincidence. Force-carrying particles are massless, most of them in the Standard Model, precisely because force needs to propagate without delay, without accumulating the energy costs of a massive carrier. The masslessness and the speed are the same property, expressed differently. The universe built its communication infrastructure out of things that don't experience time, which brings it back almost to where the chapter started. The moth hitting the glass, moving toward light, unable to distinguish between the light that came through something and the something it came through. There's no criticism in that. It's just operating with the information it has, which doesn't include glass as a category. What the photon tells us is that the speed of light isn't finally about speed. It's about the structure of what space-time allows, the two categories of thing it contains. Those that ride through time and those that ride along its surface. The limit between them isn't a wall posted at sea. It's the boundary between having mass and not having mass. Between existing inside time and existing outside it. Everything with mass lives below that boundary. Not unhappily, not constrained in any way that affects ordinary life, but below it, always, with the surface of things unreachable overhead, and the photons skimming past in the dark on their way from somewhere to somewhere else, carrying no memory of the distance and no sense of the time. And yet the universe contains things that appear, from certain angles, to move faster than light. Not particles, not spacecraft. Things, patterns, distances, the expansion of space itself. Understanding why these don't violate the limit, why they can't, structurally can't, requires looking at what the limit actually governs and what it quietly does not. The radiator in the corner also has been making a sound for the last hour. Not a loud sound, more like someone occasionally tapping a pipe once and then stopping. Irregular enough that you keep expecting it to develop into a pattern and it never does. I've been half listening to it while working through this chapter because there's something appropriate about it. A sound that seems like it should mean something and persistently doesn't, which is roughly the experience of encountering apparent exceptions to the speed of light for the first time. They arrive looking significant. They seem briefly like cracks in the wall. And then you look at them carefully, and the Vibdrakum turns out to be a shadow. And the wall is exactly where it was, and the limit is, if anything, more solid than before. There are three categories worth sitting with. Quantum entanglement, the expansion of space, superluminal jets near black holes. Each one has been brandished at some point as evidence of faster-than-light something. Each one dissolves under the right kind of attention, but they don't dissolve the same way, and the way each one dissolves is different enough that working through them separately is worth the time. Start with entanglement because it's the one that gets invoked most often and carries the most conceptual baggage. Two particles, produced together in a way that links their quantum states, their spins, say, or their polarizations, separated by any distance, measured simultaneously or close enough that no signal travelling at light speed could connect the two measurements. When you measure one and find its spin pointing up, the other's spin is instantly determined to point down, not correlated in the sense that they were always that way, and you just didn't know. Genuinely, in the language of quantum mechanics, the measurement of one affects the state of the other. The word Adderley is doing enormous work there, and it's the word everyone catches on instantly, across any distance, faster than light could travel between them, and the correlation is real. This is not a theoretical nicety. It has been tested in experiments with increasing rigour since the 1970s, most decisively in a series of loophole-free Bell tests in the 2000s. The correlations exist, are stronger than any local hidden variable theory can explain, and they appear instantaneously regardless of separation. So, faster than light? No, and the reason is specific and worth understanding rather than just accepting. What travels instantaneously, and if travels is even the right word, which I'm not sure it is the correlation, the relationship between outcomes, not information, not a signal, not any physical quantity you could encode a message in. When you measure your particle and get up, you learn that the distant particle is down, but you cannot control what outcome your measurement produces. The result is random. The distant experimenter, looking at their own random results, sees nothing unusual, just random outcomes, distributed exactly as quantum mechanics predicts for an isolated particle. Only when the two sets of results are later compared through a classical channel, through an ordinary slower-than-light communication, do the correlations become visible. There is no way to use entanglement to send a message, no way to encode information in the correlated outcomes, because the outcomes on each end are individually random and uncontrollable. The instantaneous connection is real. The information transfer is zero. It's not that the universe is sneaking a signal through faster than light. It's that what's happening isn't a signal. It's something else. Something that quantum mechanics describes mathematically, but this doesn't have a clean classical analogue. And that something else, whatever it is, doesn't carry information, and therefore doesn't violate causality, and therefore doesn't touch the speed limit. I find this genuinely not satisfying exactly, more like I find it honest. The universe gets to be strange without breaking its own rules. The expansion of space is a different animal entirely. The universe is expanding. Galaxies are receding from us and from each other, not because they're moving through space in the conventional sense, but because the space between them is growing. The metric, the stuff that distances are measured in, is stretching, and at large enough distances, the rate at which that stretching adds to the separation between 2 points exceeds the speed of light. There are galaxies, right now, receding from us at several times the speed of light, not approaching C from below, exceeding it. The most distant observable galaxies are moving away at roughly 3 times C. This one sounds worse than entanglement. It sounds like a direct, unambiguous violation. Galaxies going faster than light. Except the speed limit governs motion through space, not motion of space. The distinction is, I keep wanting to call it subtle, but it isn't really subtle, it's just unfamiliar. Special relativity describes how objects behave in flat, static space-time. It sets a limit on how fast something can move relative to something else within the same local region of space-time. It says nothing about the rate at which space itself can expand because space expanding is not an object moving. There is no reference frame from which the expansion can be observed as motion in the relativistic sense. No speedometer you could attach to a galaxy and read off a velocity that violates anything. The recessional velocities of distant galaxies are not velocities in the special relativistic sense. They are rates of change of distance caused by metric expansion, and metric expansion is governed by general relativity, which contains no prohibition on how fast the metric can change. The C limit lives inside spacetime. The expansion is something spacetime does. Different jurisdiction. There's a version of this that produces a genuinely strange consequence worth stopping on, because I think it's more remarkable than the apparent violation it's often used to illustrate. If a galaxy is receding from us faster than light, the light it emits toward us right now is, depending on the expansion rate between here and there, either barely making progress toward us or actually losing ground. The photons are moving toward us at see-through local space, but the space they're moving through is expanding fast enough to carry them backward in terms of absolute distance. They're swimming upstream in a river that's flowing faster than they can swim. Some of those photons will never reach us, not because they're too slow, they're moving at c, the fastest anything can move through space. But because the space they're crossing is expanding away beneath them faster than they can cross it. The observable universe has a boundary not because space ends, but because light has a finite speed, and the universe has been expanding for a finite time and some regions have been receding faster than light since shortly after the Big Bang. That boundary, the cosmological horizon, is a direct consequence of c being finite. A universe with infinite light speed would be entirely observable in principle. A universe with c finite and space expanding has regions that are permanently beyond reach, not just far, causally disconnected. Events occurring there cannot affect us, and we cannot affect them, and no exchange of any kind is possible now or ever. The speed limit applied to an expanding universe carves the observable world out of a much larger whole. The jets are the third thing, and they're the most visually dramatic, which is probably why they keep appearing in popular discussions of faster-than-light phenomena. Near certain black holes, active galactic nuclei, quasars, some gamma-ray burst sources, jets of plasma are launched along the rotational axis. Enormous, energetic, moving at a significant fraction of the speed of light, typically 0.95 c to 0.99 c for the most extreme cases. When these jets are oriented at a small angle toward us, directed nearly straight at our line of sight, they can appear from our observations to be moving faster than light. The term for this is superluminal motion. Radio astronomers have been documenting it since the 1970s. A jet component observed in the radio galaxy M87, the same galaxy whose central black hole became the first to be directly imaged in 2019, was measured moving at an apparent velocity of several times c. Not apparently. Measurably in the positions of bright knots within the jet, tracked over years of radio observations, showing displacement that, if taken at face value as a transverse velocity, would require faster-than-light motion. The resolution is geometric, and once you see it, it's almost elegant, almost in the slightly irritating way of solutions that make the problem feel like a trick question in retrospect. When a jet is pointed nearly at you and moving at high velocity, each successive emission of light has less distance to travel to reach you than the previous one, because the source is moving toward you. The pulses arrive bunched up in time. You observe a long period of actual travel compressed into a short period of arrival. The jet appears to cover large transverse distances in very short observed times, not because it's actually moving faster than light, but because the geometry of nearly toward you motion at high velocity creates an apparent compression of time that inflates the inferred transverse speed. It's a projection effect, a real one. The physics behind it is precise and verified, but a projection. The jet is not moving faster than light. It is moving close to light speed, nearly toward you, and the geometry of that situation produces an apparent velocity that exceeds c in your observations without violating anything in the underlying reality. Here is the metaphor, placed here, because the three cases together have set it up. Imagine a rule that governs how fast a fish can swim. The rule is real. Fish obey it. Now imagine someone pointing to a ripple on the water's surface and saying, "That ripple moved faster than any fish could swim," and someone else pointing to the far bank of the river moving away as the river floods. The bank is receding faster than the fish rule allows, and a third person standing at an angle pointing to a fish swimming toward them. Look how fast that fish seems to be moving across my field of view. None of these break the swimming rule. The ripple isn't a fish. The bank isn't swimming. The apparent crossing speed is geometry, not speed. The second use of this metaphor is the place where it breaks, deliberately. Because unlike fish, the speed limit for light isn't just a biological constraint on a category of thing. It's a geometric property of the medium itself. The river, in this case, is also subject to the rule, not in the same way the fish are, but in a deeper way, a way that means the rule and the river are made of the same stuff, which the fish analogy cannot carry. So I'll let it go here. What the three cases have in common, entanglement, expansion, superluminal jets, is that they each fail to violate the limit for reasons that reveal something about what the limit actually governs. It governs information, causality, the ability of one event to influence another. It governs the local relationship between two things in the same patch of space and time. It does not govern correlations with no information content. It does not govern the metric expanding on scales where local physics doesn't apply. It does not govern the geometry of how approaching sources appear to a distant observer. The rule is precise, more precise than nothing can go faster than light, more like no causal influence can propagate faster than light, no information, no signal, no physical effect that allows one event to depend on another outside the light cone. Everything else the universe gets to do, and it does quite a lot. I keep thinking about this and arriving at the same place, which is that the speed of light limit is, the word I want is conservative, not in a political sense, in the sense of being precisely as restrictive as it needs to be, and not one bit more. It closes exactly the doors that would produce paradoxes. It leaves open everything that doesn't produce paradoxes. Entanglement can be non-local because it carries no information. Space can expand superluminally because that expansion transmits no signal. Jets can appear to move faster than light because appearances aren't velocities. The limit is a surgeon, not a blunt instrument. Is that? I'm not sure that's the right framing. Maybe I'm projecting a kind of elegance onto something that's just a consequence of geometry, with no intent behind it. Probably. But the precision of it stays with me regardless of whether the precision is meant. There is one more thing, not an exception, not an apparent violation, something older and simpler, and, in its way, more fundamental than any of the cases in this chapter. What the speed limit is made of, at its most basic level, not as a law imposed, not as a consequence derived, but as a description of what space and time are when you look at them without the assumptions. That's where this ends. The candle has been burning for about 40 minutes now. One of those wide, low ones that pools wax almost immediately and produces more light than you expect from something that small. The flame doesn't move much, just a slow lean in whatever direction the air is barely moving, correcting, leaning again. It's the kind of thing you watch without deciding to watch it, and there's something in the constancy of it, the flame going nowhere, maintaining itself against the slow consumption of what it feeds on, that feels right for this chapter, though I couldn't tell you exactly why. We've been at this for a while now, Roma and his stubborn moon, Bradley and the tilted sky, Michelson and the null result that wouldn't explain itself, a teenager's thought experiment that sat unresolved for a decade, a paper that removed the floorboard from time and then calmly listed what follows, the energy costs that become infinite before the destination, the massless things that exist only in motion, the apparent violations that dissolve, and underneath all of it, the same number, the same speed, constant, everywhere, always, for every observer, in every frame, regardless of how fast the source moves or how fast you move toward it or away from it or sideways relative to it. 299,792,458 meters per second. It never changes. That constancy is not the conclusion of this story. It's the material the story is made from. The question this chapter wants to sit with, not answer, not resolve, just sit with, is what that constancy actually is, what it's built from, what kind of thing the universe had to be for that number to be what it is. Start with what the limit is not. It is not a rule appended to reality from outside. There is no cosmic legislation that says thou shalt not exceed 299,792,458 meters per second, posted somewhere upstream of the equations and enforced by some mechanism we haven't found yet. That framing, which is probably the most natural one, the one the word limit encourages, implies that faster than light travel will be possible in some structural sense but is prohibited. Possible but forbidden. The prohibition doing the work of prevention. That's not what's happening. When you follow the mathematics of special relativity to the point where a massive object approaches C, what you find is not a prohibition. You find an incoherence. The equations don't say, stop here. They say the thing you're describing stops making sense here. A massive object at the speed of light doesn't violate a rule. It violates the definition of what a massive object is. The situation is not forbidden. It is undefined. Like a question with no answer, rather than a question with an answer you're not allowed to know. The difference matters. Forbidden things exist, in principle, in some conceptual space outside the law. Undefined things don't exist anywhere. There is no version of reality, even a hypothetical one, even a thought experiment, even a mathematical toy universe, in which a massive object moves at c. The concept doesn't cash out. It's not a locked door. It's the absence of a door entirely, just wall all the way across. Here is where space-time geometry enters, and I want to approach it carefully because it's easy to reach for it as an explanation and have it feel like a deeper-sounding version of the same assertion. The structure of space-time prevents it can mean something rigorous, or it can be a fancy way of saying because it can't. I want to try for the rigorous version, even if incompletely. In special relativity, the universe has 4 dimensions, 3 of space, 1 of time, and the relationship between these dimensions, the geometry of how they combine, is described by the Minkowski metric. Not Euclidean geometry, where distance between 2 points is the square root of the sum of squared spatial separations. Minkowski geometry, where the space-time interval between 2 events is calculated differently, You square the time separation, subtract the squared spatial separation divided by c squared, and take the square root of that. The minus sign is everything. It's what makes space-time different from ordinary four-dimensional space. It's what makes time not just a fourth spatial direction. The space-time interval between two events can be three things. Positive, time-like, meaning a slower-than-light connection exists between them. Zero, null, or light-like, meaning they can be connected only by something travelling at exactly c. Negative, space-like, meaning no causal connection is possible, because reaching one from the other would require faster-than-light travel. The speed of light is the boundary between time-like and space-like, between causally connectable and causally disconnected. It's not a speed that particles happen to not exceed. It's the geometric feature of space-time that separates the region where cause and effect is meaningful from the region where it isn't. It's the edge of the causal structure of the universe. I want to call it beautiful, but that word has been worn thin. It's more that it's load-bearing in a way that feels almost architectural. The speed of light isn't fast. It's a property of the shape of things. There's a version of this that comes from a completely different direction, not from particles and accelerators and Lorentz transformations, but from electromagnetism. From Maxwell's equations, which predate Einstein by 40 years, and which contain buried in their structure a wave that propagates at a speed determined entirely by two constants of nature, the permittivity of free space and the permeability of free space, constants that describe how electric and magnetic fields interact with vacuum. Constants that were measured in the laboratory from tabletop experiments with coils and capacitors. You divide permeability into a specific combination with permittivity, and you get C, exactly C, without any reference to relativity, without any reference to reference frames or observers, or thought experiments on trains. Just the electromagnetic properties of empty space combined in a specific mathematical way, producing the speed of light directly, which means c was in the fabric of empty space before anyone thought of it as a speed limit. Before special relativity, before Michelson-Morley, before Romer, the constants that determine how fields propagate through vacuum determine how fast light moves. And because those constants are the same everywhere, because the vacuum doesn't vary from place to place in its electromagnetic properties, the speed is the same everywhere. The constancy of c isn't a coincidence of how we measure things. It reflects the uniformity of the vacuum itself. The speed of light is what it is because empty space is what it is. And here is where, if you follow the thread far enough, something else surfaces. Something that I find genuinely difficult to fully hold, and I say that not as rhetorical humility, but because I have sat with this specific idea many times, and it continues to resist complete absorption. The constants that appear in Maxwell's equations, the permittivity and permeability of free space, are, in the modern understanding of quantum field theory, properties of the quantum vacuum. Not of nothing. The quantum vacuum is not empty. It's a seething, fluctuating substrate of virtual particle pairs, borrowing energy from uncertainty, existing briefly, annihilating, leaving behind a vacuum that has structure, that has energy, that has measurable properties. The Casimir effect, the tiny attractive force between two uncharged metal plates placed very close together, is a direct measurement of this vacuum energy, demonstrated in laboratory conditions since 1997. The permittivity and permeability of space are properties of this quantum vacuum. They describe how that structured nothingness responds to electromagnetic disturbance. And from those responses, from those properties of what empty space is made of, comes C. the speed of light as a consequence of the quantum mechanical structure of the vacuum. The speed limit followed deep enough is a property of nothing. Or, more precisely, and this is where I want to be careful not to overclaim, it's a property of what nothing turns out to be when you look at it closely enough. The vacuum is not a simple absence. It has properties, it has a structure, and one of those structural properties, working through electromagnetism and geometry, produces the speed at which information can travel, at which causality can operate, at which light moves. Here is the metaphor, placed here, used carefully. Think of a medium with a particular density, not water exactly, just some hypothetical medium with some particular physical character. Waves move through it at a speed determined by that character. Change the density and the wave speed changes. The wave speed is not a property of the wave, it's a property of the medium. The speed of light is something like the wave speed of the universe's own fabric. It emerges from what space-time and the quantum vacuum are, not from what light is. Light doesn't decide to move at c. Light moves at c because that's what the medium permits, demands, really, for a massless electromagnetic disturbance. And the limit on all other things reaching c is not, at this level, about those things being forbidden. It's about what it would mean to move faster than the medium allows, which is, and here the metaphor genuinely breaks, the way they all do at the edge of where analogies can carry weight. Not a thing the medium contains a description for. The medium sets the speed sets the geometry sets what causality means, and causality sets what a universe with a coherent before and after even is. Pull one thread and you're holding all of them. The candle is lower now than when I started, not much, maybe a few millimeters of wax consumed in the time this chapter has taken. The flame still leans in the barely moving air, still corrects, still maintains itself. Doing what it does at the rate it does it, which is determined by the chemical character of the wax, the oxygen content of the air in this room, the temperature of the wick. Nothing mysterious, nothing arbitrary, just the thing it is doing what things of its kind do in conditions like these. I keep returning at the end of all of this, not to the number, not to 299,792,458, but to the constancy, the fact that it doesn't change, that every observer, in every frame, in every corner of the observable universe, measuring the speed of light in vacuum, gets the same answer. That this sameness is not a coincidence, not an approximation, not a working assumption that might break down at extreme scales. That it's structural, that it reflects something about the uniformity of the vacuum, the geometry of space-time, the relationship between mass and energy and motion that goes all the way down to whatever the bottom is. We started in the first chapter with a question about what kind of limit this is. Not a rule posted from outside, not a ceiling engineered by some mechanism, something the universe is made of. That's still where it ends. Not with more certainty than before. I don't think sitting with this honestly produces certainty, or should, but with a better sense of the shape of the thing. The limit is everywhere because it comes from everything, from the electromagnetic character of empty space, from the geometry of how time and distance combine, from the way energy and mass are the same substance under different conditions, from the causal structure that makes before and after mean what they mean. The speed of light is the rate at which the universe talks to itself, and it cannot go faster, not because it's held back, but because that speed is what the conversation is made of. This channel and everything it makes runs on no external funding, no network, no studio, no institutional support, just the work and the people who quietly choose to back it. If these nights of slow science mean something to you, and you want to help keep them going, Patreon is where that happens. It's a genuinely self-funded project, and every contribution carries more weight than it probably should. Thank you for being here for this one.